Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 30th, 2026, just 3 days ago. It introduces a fully quantized training scheme that achieves up to a 4.2 times speedup on NVIDIA Blackwell GPUs, while significantly reducing the error usually seen in low-precision training. The paper is titled Quartet 2, Accurate LLM Pre-Training in NVFP4 by Improved Unbiased Gradient Estimation. And as we'll see later, the results for end-to-end model training are quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 breaks down how quantization affects validation loss. The vertical axis shows loss increase over a BF16 baseline, where lower values are better. Red lines here represent standard stochastic rounding, while blue lines show the new micro-Eden method. Focusing on panel E at the far right, which represents fully quantized backward passes, we see the blue lines stay significantly lower. This confirms that micro-Eden prevents the large errors that typically plague standard rounding methods. Table 1 provides the hard numbers backing this up. It compares the mean squared error, or MSE, across various rounding schemes using normal distribution data. Notice the trade-off in the bottom section. Standard stochastic rounding, or SR, is unbiased, which is vital for training stability, but it incurs a massive error of 23.5. However, the MS-Eden method in the last row solves this. It remains unbiased, yet drops the error significantly to 9.8, effectively giving us the best of both worlds. So while Table 1 settled the backward pass, Figure 2 optimizes the forward pass. These charts track validation loss increase relative to a BF16 baseline, where lower lines mean better accuracy. The red lines at the top represent standard square block quantization, which clearly lags behind. In contrast, the blue lines at the bottom show the proposed approach, combining native 1/16 blocks with the 4/6 heuristic. Since this blue configuration minimizes error across all model sizes, it becomes the choice for the Quartet 2 forward pass. Alright, effectively combining those insights, Figure 3 illustrates the complete Quartet 2 computation graph. The top path handles the forward pass, where activations and weights use the 4/6 round to nearest strategy to feed the efficient N versus FP4 gem units. However, the real complexity lies in the backward pass shown in the striped blocks below. Here, gradients and weights are processed with Hadamard transforms and MS-Eden quantization. This rigorous pipeline ensures that despite the low 4-bit precision, the gradient estimates remain unbiased before reaching the optimizer in the center. Now, Figure 6 translates those architectural choices into raw performance. This chart reports the speedup of linear layers over a BF16 baseline, organized by model size from left to right. The towering blue bars represent Quartet 2 using the N versus FP4 format. You can see a clear trend where the advantage grows with scale. For the 22 billion parameter model on the far right, the speedup exceeds 4 times. This significant jump over the red and green baselines confirms that the new kernel optimizations deliver major efficiency gains. So, while Figure 6 showed the speed, Table 5 confirms the quality. It reports the final bits per byte, or BPB, for 2 model scales, a 560 million parameter model on the left and a 1.9 billion parameter model on the right. Looking at the pre-training section, the bold numbers highlight that Quartet 2 yields the lowest increase in validation loss compared to the BF16 baseline. For the larger model on the right, the penalty is only 1.44%, which is a solid improvement over the 1.7 to 1.9% range seen with previous methods like TetraJet V2. Wrapping up, the big hook here is that Quartet 2 effectively closes the gap between low-precision hardware and high-precision results. By shifting stochasticity from individual elements to microscales, it makes 4-bit training viable for massive models without the usual accuracy penalty. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.